Welcome to Building Reliable Data Lakes with Delta Lake. My name is Denny Lee. I'm a senior staff developer advocate here at Databricks. Been here since 2015 or so. Been working with Apache Spark since 0.6 and Delta Lake since its inception. Prior to that, I was a senior director of data science engineering at SAP Concur and a principal program manager at Microsoft for Azure Cosmos DB, Project Isotope, which is what is currently known as Azure HD Insight, as well as SQL Server. So why are you here? Let's talk about it. It's a Delta Lake, an open source storage format that brings ACID transactions to big data workloads on cloud object stores. It's the key ingredient for building lakehouses. So let's talk about that evolution of data management. Why do we even need lakehouses in the first place? Well, first, let's start with data warehouses. And I'm actually from that era, by the way. So I don't know if I look it, but I certainly feel it, okay? And what happens here is that I was part of the SQL Server team, and we were boosting this idea that the data warehouse would allow us to do everything. We would build these OLTP transaction databases, do some ETL. I apologize in advance for my involvement with the SQL Server Integration Services and DTS for any of the folks that end up using it. And we push all of this data into data warehouses, which was great, right? Because that meant I could throw my BI, my reporting. So again, you want to blame me for, or partially blame me for SQL Server reporting services or SQL Server analysis services for your BI. Yes, I was there during those days as well, helping to build those systems. They were great, right? Except, and that's the key thing, there wasn't support for video, audio, or text. There's no support for data science and machine learning. Even this idea that we could potentially use cursors or functions within Python functions or R functions directly within the database was problematic at best. There's limited support for streaming. Some different companies actually did try to provide streaming capability within warehouses, but it was very, very complicated. And the most important aspect, it was a closed and proprietary formats. These systems themselves were not open. They were built, it's a closed silo, closed house that ensured that it was that you would only utilize that particular data warehouse, and it was really expensive to scale out. And therefore, right now, when we switched to data lakes, most data stored in data lakes and blob stores because we wanted that flexibility. And so I was actually part of that transition as well, because I was part of the crew that said, hey, we need to build Hadoop, Hadoop on Windows originally first, and then afterwards Azure Hadoop. So in other words, Hadoop on Linux, but in the Azure cloud. And we really pushed that idea of like schema on read. Yes, we could do everything with schema on read. We wouldn't care about the structure of the data. We didn't need a schema anymore. We would just simply go ahead and determine the schema at that point of read time, right? And no problem at all. And of course, to anybody that's in this particular conference, that's not true at all, okay? So, but that was the idea that data lakes could handle all of your data for data science and machine learning, but really poor BI support. Any systems that want a BI, so for example, if I wanted Trino to go ahead and read a data lake, if I didn't have a schema, that's a horrible thing to actually have, right? It's super complex to set up at times. More often than not, extremely poor performance and unreliable data swamps. Now, some people call it data swamps, some people call it data salad. Doesn't matter what the nomenclature is. What it meant is that you had a lot of data stored in these cloud object stores or HDFS, i.e. data lakes, in which there was no lineage or control over this data. Nobody seemed to understand what was going on. It did give you the flexibility to store structured, semi-structured, and unstructured data. It did give you the ability to store text, audio, video. But what ended up happening is that it became a much more complicated system to deal with in order to get to data science, machine learning, and real-time databases. And if the schemas of your data could not be trusted, the old adage of garbage in, garbage out, you don't really know what you're seeing. And so the idea of coexistence. So the idea of saying, okay, no, we'll have a data warehouse on one side and we'll have a data lake on the other side and everything will be perfectly fine. Well, how do you reconcile all of that data? how do you make sure that data is actually what you're reading out of the data warehouse and what you're reading out of data lake actually made sense, that the users themselves could actually reconcile between these two different systems? You end up having reporting by one system saying one number, another system saying another number, and technically they make sense, but they don't. And the reconciliation process ends up becoming, or validation process becomes more complicated than the actual process of processing the data. Now, that's very undesirable to say the least. And so this is the reason why we really want to bring this concept of a lake house, best of both worlds. It gives you the ability to have the flexibility of a data lake here on the right side, right-hand arrow, in which you can store structured and semi-structured and unstructured data and work with it and be able to deal with multiple paradigms like data science, machine learning, real-time databases. Yet at the same time, on the left side, it actually has some of the most important aspects of a data warehouse. I have a schema, I have structure, I have fast BI support. So that way, you can actually have a simplified reconciliation or validation process in which there is none, because the Lakehouse handles both of it for you right from the get-go. So how do you reconcile these two? Okay, so there are multiple versions of Lakehouse, and obviously today we're going to be talking about Delta Lake, but the key most important aspect, especially here in this conference of Single Neutrino, is that you really need this concept of somewhere in between where you have a Delta Lake for a data lake, excuse me, data lake for all your data, and one platform for every use. Okay, you need somewhere in between. Okay, and how you do that is with Delta Lake. Okay, scalable, open, general purpose transactional data format. All right, that's a fundamental concept in order for us to be able to do it. And then in order to add on top of it, with Delta Lake, obviously we're going to showcase Trino today, but that's the call out, the high performance query engine that talks to Delta Lake in order to give you the best of both worlds. You need these two concepts. You need Trino for the high performance query engine, and you need Delta Lake to give you that scalable, general purpose transactional data format. So let's go backwards a little bit and ask the question of, in Delta Lake, the architecture. Why is it scalable? How does it actually give you that context? Well, Delta Lake equals this concept of scalable storage for data, as well as scalable transaction log for metadata. You actually need those two things, because as your transaction log or as your metadata grows, it actually has to be able to scale as well. And so how do we do it? Well, let's talk about the scalable storage concept first. The table data is stored as Parquet files on cloud storage. All right. So in other words, your standard open source Parquet files, that's exactly what's inside your Delta Lake table itself. Okay. So in other words, for example, you have your path to table, you have your 0, 0, 0, 0, 1, 0, 2 Parquet files. These are the Parquet files that make up your scalable storage. They're sitting on cloud object storage, so that way they can scale appropriately, okay? But as many as you probably know, the biggest problem when it comes to cloud object storage is the list operation itself is extremely slow. So if I have millions upon millions of files, okay, of these Parquet files that I have to traverse through, that list operation becomes excessively slow. And when it comes slow, I mean, as in the query performance, for example, if Trino's trying to query that data, if I was to list all the Parquet files, man, that would significantly slow down the performance because it's just waiting on that list operation. So how do I speed things up? Well, I speed them up by having a scalable transaction log. Okay, so inside that same folder, there's an _delta_log. Okay, and so inside there is a bunch of JSON files. Okay, plus those are .jsons, these are one.json. So it's basically a sequence of metadata files, these JSON files, to track operations made on the files in the table. Now, these are, like I said, they're stored in the cloud storage along with the table, and they allow you to read and process the metadata in parallel. That's an important aspect. So when you look at the Trino connector, for example, when it's accessing a Delta Lake table, it's able to go ahead and read those JSON files. And by the way, there's every 10th is a checkpoint, which is a Parquet file. So it'll just read the Parquet files. But the idea is that it's actually able to read those files quickly, understand what inside those JSON/Parquet files in the Delta log, that is, it includes a list of every single Parquet file that makes up the table. Not every single Parquet file that's inside the Cloud Object Store actually makes up the table, at least for that particular snapshot. I'll talk about that concept in a little bit more in a second. But the idea is that every single Parquet file that is inside the Cloud Object Store does not necessarily translate to what the table is at the time, because Delta Lake also includes time travel, the ability to basically go ahead and go back in time and look what the earlier version of the table is. So based on the metadata that you're reading, for example, if I'm looking at the most recent snapshot of the data, it'll contain all the Parquet files that make up the current table. If I was to go back in time, it would actually tell me all the Parquet files that actually made up that version of the table at that time. So instead of actually doing that file listing from Cloud Object Stores, it's just simply reading a single Parquet or set of JSON files to determine what makes up that table. Then Trino is able to go ahead and quickly send its worker nodes to go ahead and query the data directly. All right. So that way they can know exactly which Parquet files it's supposed to hit in order to read that data. So really powerful way for you to scale both the storage and the transaction log itself. Okay. So let's talk about that. Why is this transaction log so important? Well, it's because it's going back to your database days. It's about transaction log commits. Changes to the table are ordered and they're atomic commits. Okay, this is very important. Okay, so in other words, it allows you to have that ACID transaction that's so important. That's versus if you were to go ahead and read and write directly to a Parquet file directly to a data lake in general, you would not have that. And what do I mean by that? What I mean is this. You're running a job. Doesn't matter which distributed system. Could be Trino, could be Spark. It doesn't really matter. Just you're running some job itself. It's writing files in mid-flight. Okay, but the job fails. What happens? Well, if there were, let's say, 20 tasks executed at that time to actually write all those files, what happens is that, let's just say, the 19th task fails. Well, that means 18 files were most likely already written to the Cloud Object Store. All right. Well, then what happens to that 19th file? Okay, well, the 19th file failed. So now what you have is a bunch of orphaned files, a bunch of files that are written in the Cloud Object Store in the same location that you don't know if they're supposed to be there or not, right? Well, that's what the transaction log does. The transaction log allows us to know, are those files that were written supposed to be there or not? So just in case there was a failure, the transaction log itself would have failed. Okay, which means that it would not have been committed to transaction log. So even if there are those 18 files there, we would never read them because we knew we would only reference the transaction log to determine what files you're supposed to read. Okay, so this allows us to do when you're trying to process lots of data and write lots of data, whether it's batch or streaming to the Cloud Object Store at any one point in time. It's writing these JSON files that is the final commit that lets us know what's going on. So for example, if I'm doing an insert action, I'm inserting data into my Delta Lake. Okay, well, for example, using this green here, I added 001 and 002 Parquet files in 000.json, the 0th JSON. Okay, perfect. So now we know that if I was to read the table at the point in time where you're saying, okay, because it's a couple milliseconds before 001 JSON got written, right? I don't want any dirty reads. Okay, what is the snapshot at that point in time that I went ahead and ran the query? I'm only supposed to read 01 and 02 Parquet files. A few seconds later, I do an update. That update goes ahead and generates a 03.parquet file and ends up removing 0102 Parquet files. Okay, no problem. Any query, whether it's a read, write, or update or modification that happens after the update action, instead we'll see the 01.json file. And because it sees that, the listing of files will only include 03 Parquet. It will not include 01 and it will not include 02. Okay, so that's pretty cool because that way, if you had a query that ran right after 0.json and you had another query that ran right after 01.json, you know exactly which files and you're not risking any dirty reads at that point in time, because this is actually for short running queries, that probably is not that big of a deal, honestly, because you'll probably just generate right off the 01. But for long running queries, this actually is a big deal because you want to know what the status of the data was at the time that you queried it. Okay. And so that's why it's important that every single atomic commit goes as a JSON file within that Delta log folder. Okay. Set of actions, as you can see here. All right. But in order to keep that consistent snapshots, like I said, this actually I just described it for you. So that the readers, whenever they're reading, they're going to read those atomic units. So they actually will see those 0.json or 0.1.json. So that example that I just gave you, right? If it happened, let's just say at 1 o'clock, it was 0.json. At 2 o'clock, it's 0.1.json, just for the simplicity of this example that I'm speaking to you. What will happen is basically any query that happens between 1 o'clock and 1:59:59.999 seconds, it'll actually ensure it reads the 0102 parquet files, right, from the insert action. But at 2 o'clock, when the 01 JSON gets committed, it'll only read the 03 parquet files. And so the readers, any of the readers, to ensure consistency, it'll only read either 01 and 02 parquet or 03 parquet, but nothing in between, excuse me, okay? Because that way you have consistency when you're reading your data, okay? And so when we talk about ACID transactions via mutual exclusion on those log commits, what has to actually happen is that the concurrent writers have to agree on the order of changes. So we actually follow the optimistic concurrency control that we basically are choosing to say, or if you're able to go ahead and write to the to your Delta Lake, for sake of argument, to different partitions of data. So one's doing an update to partition 0, while one's doing an insert to partition 2. That's fine. That's optimistic concurrency control will allow that right to happen because we're saying they're actually not interfering with each other. But if you're actually trying to update the same partition of data as you're trying to insert, okay, there may in fact be problems because you need to know exactly which order. Did you update this first and then you insert the data, or did you insert the data, which the update itself might actually impact, okay? So these new commit files will be created mutually exclusively from each other using storage-specific API guarantees, okay? So for example, writer 1 is going ahead and trying to write to 0.json, okay? Meanwhile, writer 2 is actually going ahead and try to write to 0.1.json. But then both writer 1 and writer 2 are both trying to write to 0.2.json at the exact same time. Only one of them is going to succeed. In this case, it's writer 2, but you never know, maybe writer 1 would have won. But either way, it doesn't matter. Only one of them succeeds. And then writer 1 will actually try again. Because this is an important aspect of atomicity. We have to make sure whatever's being written is consistent at that point in time. There's only one of them that's allowed doing commit at that point in time. So even with all of our discussions about parallelism, at some point, there is a serial point where basically we have to make a decision, which one's committing, which one succeeds, and only one gets the rule in this case, okay? Oops, sorry. All right. So when you look at the same storage system support, Delta relies on the scalable cloud storage infrastructure for an ACID guarantee. So remember, it's relying actually on S3 itself. It's running on Azure Blob Storage, Azure Data Lake Storage Gen 2, excuse me, or Google Cloud Storage. So that way there is no single point of failure and it's production ready, okay? And so the storage system support, just call that out. But with S3, there is one call out, okay, that actually in order to ensure, because S3 itself lacks put if absent consistency guarantees, what happens is that we actually need a lock store. Which one's locking first in order for us to write to the log store? In this case, with S3, we're also using DynamoDB as well. It's commonly used for other storage formats as well, but so we're following the same thing. It was just released actually in Delta 1.2 with our friends over at Samba TV to go ahead and do that contribution. So it's pretty cool. All right. So what does it make it? What does Delta make it Delta Lake? What features make Delta Lake unique? Well, in addition to the fact that we're talking about ACID transactions and we talked about things like scalable metadata, we also have the ability to do time travel and audit history. In other words, we can revert to earlier versions of the data, and we can actually log all transactions that happen to the Delta Lake to provide you a full audit trail. And so that's pretty cool. So remember how we had the 001, 02, and then 003? Well, the things that, how about if you wanted to look at the previous data? Well, after the at 2 p.m., if I want to look at the version 1 data, no problem. The Parquet files are still there, okay? And you just refer to a earlier version to get access to it. All of this together allows us this idea of unified batch and streaming. So the semantics of basically writing to the Cloud Object Store, or for that matter, HDFS, whether it's a batch process that's reading or writing, or if it's streaming process that's reading or writing, it doesn't matter. In fact, not only is it being utilized for structured streaming, but we actually have PRs for Pulsar and actually Flink. The Flink sync actually just came out as part of Delta Connector 0.4. There's absolutely this concept of schema evolution enforcement, this idea that you can enforce the schema to ensure that any changes to the schema cannot happen to the data unless you actually wanted it to happen. And at the same time, you can evolve the schema if it's necessary. There are things like constraints and generated columns, pretty cool concept to ensure that the data meets your semantic requirements. Actual constraints, from our database days, and generate columns, basically this idea, some people call it hidden partitioning. We think it's a little bit better because it allows you this idea that you can generate new columns based on the existing data. And then you can build your structures or your constraints based off of that. And of just as important, of course, your DML operations, data manipulation language. So you can do your updates, your merges, your deletes, whatever you want in Scala, SQL, Java, Python, whatever language you prefer. Okay, so really cool. Okay. So with the few minutes I have left, I want to talk a little bit about the roadmap. So Delta Lake has a very fast pace of innovation. So this is a massive screen, which I'm not going to go through, but it has a lot of innovations that have happened since it's 2 years since we've open sourced the project. Okay, so we're actually coming up to April. Actually, we're already April 2022. As part of Summit, we're going to be having a big splash talking about our 3-year anniversary of open sourcing Delta Lake, which is great. So there's a lot of innovations, as you can see from here. So as part of Delta Lake 1.2, which was just released, we're also including things like data skipping with column stats. We already talked about the S3 multi-cluster writes, which was great, okay? With the data skipping, I do want to call things out, right? It's the column min max values are automatically collected. And when you're writing files and committed to the log, so that way, when you're running your read queries, like from Trino, you can go ahead and skip those files. You don't have to read those files directly. Pretty sweet, okay? Also, things like compaction, the optimizing and optimize command are automatically included. For some of you, you're going to ask me the question, hey, that's great that I've got optimized, but where's optimized Z order? That's actually part of our Delta 2.0 push as well. So if you take a look at the Delta Lake GitHub issues or delta.io/roadmap, you notice it's right there, okay? You want to build to restore or roll back to previous table versions. You could do it before with some funky queries, but now we're just including the restore table function, okay? So that way makes it a lot easier. And you can also rename columns. Oh, that's right. I forgot I put this in the slide already. The optimized Z order is actually included for the remaining of the H1 roadmap of this year. Okay, so that's being included as well. So with the optimized Z order, the whole context is this idea of multi-column data clustering. That's better than just simply multi-column sorting. So we actually are clustering the data. So that way we know how to skip or read which files, so that way you're scanning less files overall. There's less false positives for you to go through, okay? Now, with column stats, this enables also the better data skipping, which also leads to faster queries. So all of this together allows us this much faster performance. Okay, and then, other things that we definitely want to be adding, things like generate the change data feed. Change data feed is a popular feature that's also being included as part of the roadmap, as well as drop columns. Like I said, these slides, by the way, will be available to everybody. So if you want to see the full roadmap items, just look at the GitHub issue or go to delta.io/roadmap. And then in terms of the connector ecosystem, with the few minutes that I've got left, as you can tell, Delta Lake has multiple API languages, Scala, Ruby, Python, multiple cloud platforms, multiple SQL engines, and ETL and streaming engines, okay? So lots of different systems that are all working together, that all work well, extremely well with Delta Lake. And there's even more integrations. Some calls outs, we're calling out the Presto, Trino, Flink ones that were just recently released, so that's why I wanted to call those out. What's else? Oh, community adoption. Oops, sorry. There we go. So to give you some context of the incredible scale of Delta Lake, we're talking about 450 petabytes of data processed each day. And within the Databricks environment, we're talking about 75% of the data scanned is all in Delta Lake, and more than 5,000 customers in production. And actually, when we go ahead and talk about more in Delta 2.0 for the Data and AI Summit, yeah, we're actually going to be telling you even more larger numbers because these are last year's numbers, which is pretty cool. But how do you want to engage with us? Well, there's multiple ways to engage with us. There's the Delta.io website, there's the Slack, Google group, YouTube channel, GitHub issues, LinkedIn, the meetups, right? There are multiple ways to engage with us. And don't forget, we have community office hours every 2 weeks. Okay. So for example, this one's from February 17th, included Apple's Dominique Brzezinski, who's actually talking about how he had contributed to Delta Lake. And then finally, most important, how do I use Delta Lake? Well, for us Cinco de Trino folks, just go to go.delta.io/Trino. Okay. That actually goes directly to the Trino Delta Lake page to give you all the information you need to get Trino up and running in Delta Lake. And as well, like I said before, there's multiple ways to engage with us. You can start with the Delta.io page and all the different ways to engage us with us there. And with that, I appreciate your time. Thank you very much. I'll go ahead and probably answer some questions now. So that's it for now.